Our next speaker is Nati Srebro from TTI. He's promised to piss off at least 2 members of the audience. Ben,
No.
trigger warning.
Okay, so isn't okay, I'm just gonna. Okay, great, thanks. So I'm gonna, thanks for Tommy, because I'm gonna launch straight into trying to address some of the questions he raised and partly repeat what he said. I should say this is what I'm gonna try to do. There are lots of, there's lots of work we've been trying to do in the past few years trying to understand deep learning, which I hopefully will have time to touch on towards the end of the talk, but I want to spend most of the time actually not so much talking about the progress we've made, but more talking about what are the answers, what are the questions that need to be answered, and why did we even, why we started on this path. So as we saw already yesterday in Amnon's talk and today, this morning, Tommy directly referred to these questions. In order to understand the learning system, to some extent we have to answer 3 basic questions. So we have to understand, first of all, what is the capacity of this learning system? And if this system has infinite capacity, we can't learn with it. This roughly would tell us, how many examples do we need in order to be able to generalize. We have to understand this for deep learning. A traditional view, at least, of deep learning, if we look at 1990s deep learning, we actually have a very good understanding of what is the capacity of a neural net. So roughly speaking, the capacity of the neural net is given by the number of parameters in the network, the number of edges in the network. And actually, if you look at it a bit more finely, it's maybe a bit more, but we do have a very good understanding of this, and for the purpose, at least, of this talk, it's fine to think of it just as the number of parameters in the network, number of edges in the network. And the second thing we should ask is, how expressive are these things? We're going to learn by fitting a deep network. What can we capture? Can we actually capture reality? And this is maybe sort of the main question people think about when thinking about deep networks. So one answer to this is that we can capture everything, right? So deep network with a neural net, even a 2-layer neural net, I can approximate any function. Right? So in that sense, deep networks are great. I mean, I can bound their capacity, I can represent everything, so I can learn everything. Now there's of course a catch here, because when we say that we can approximate every function, that's true, but we can approximate every function with a huge network. Right? The size of the network increases exponentially with the dimension if we want to approximate a function over d variables. And so if we couple that with our capacity control, that becomes useless. I mean, because in order to have capacity control, the traditional view tells us we have to have a small network. And so really what we should ask is not what can neural networks approximate, which is what traditional approximation theory for neural net tells us, but what can neural networks approximate with small size? What can small neural networks approximate? Okay, fine. So now we can have, there's lots of work that says that lots of natural, interesting phenomena are well approximated by small, deep networks. Okay? And this, we can talk about both embedding various classes in there. We can talk about how it captures, say, visual phenomena, because we can have this hierarchy between the levels, and the lower levels can capture, even if we have a small number of edges, the lower levels can capture low-level features, and then we can gradually have higher-level features, and we can really represent lots of stuff. But the truth is that we don't need all this, because we do know that to some extent, even small neural networks can capture everything. And what I mean by everything, well, they can capture anything we can compute in bounded time, in time t. And I would claim that I would never want to learn something that I cannot represent by a function that can run in bounded time. Because, I mean, what's the point of learning, from my perspective at least? The point of learning is being lazy and replacing programming. So instead of programming, hand coding some system, I'm going to feed a bunch of data into my learning algorithm and get out of it a system that actually performs the task. What I'm talking here is what is the runtime of the resulting system. If there's no possible resulting system to perform my task is just impossible. Not the learning task, but the actual task I'm trying to learn how to do, then there's no point in learning in the first place. So from my perspective, and I think this is the general approach to learning, if we can learn everything that's computable in a short time, that would be great. And in fact, neural networks can represent efficiently everything that's computable in time t with a network of size roughly t, and it gets to exactly what is your model of computation to tell you exactly what does it mean roughly t. So if I look only at the capacity and the expressive power, that means that neural networks are, in fact, when I understand deep learning completely, and I understand why deep learning is, in fact, a universal learning machine, it's great. I can express anything I want, and anything I would ever want with a small network, and I only need a small number of samples in order to learn it. And so, in fact, if I could actually train deep models, like take a data and find the neural net that best fits them, I could learn anything. Okay? The only problem here, and this would be a completely satisfactory answer if we're only thinking in terms of like statistics and completely ignoring computation. The only subtle point is that we cannot ignore computation, right? We actually want to actually have some method of finding a network that fits data. And that's not so easy. So for example, we know that just the problem of given data finding a network that best fits it is NP hard, even for a tiny, tiny network, even for a network with just 2 hidden units. Okay? But now you can say, well, okay, fine, but what if I don't need to exactly fit it, maybe it's fine to approximately fit it. And also maybe what's NP hard is if I have data generated by the network with 2 hidden units, then fitting it with a network with 2 hidden units. But what if I say, okay, I'm fine with making my network size much, much larger, right? So many of the explanation for deep learning talk about overparameterizations and say, okay, I think my reality is captured by a mid-sized neural net. Some neural net would say just like 1,000 units, and instead I'm going to fit it with 3,000 units or 10,000 units, and maybe that makes it easy. Or maybe there's some other method of like capturing something represented by neural nets. Unfortunately, we know that that's not the case. So we have very strong hardness results. And when I say we, I should say the community. I mean, this is not me personally. Okay? We have very strong hardness results that tells us that even if reality, even if we have data that's exactly captured, with no error, and this would of course hold even if they're approximately captured, exactly captured by a single hidden layer neural network with a moderate size of units, any superlinear, think of it as any logarithmic number of units, okay? Then there is no method whatsoever, okay? No efficient method, no polytime method whatsoever that will succeed in actually no matter what model you fit, there's no method that will be able to get you error much better than chance. Okay? So training deep networks really is provably impossible. Okay? So we see lots of work saying, oh, we train deep networks, but I just told you we can do that. Okay? And from my perspective, this is probably the main, if you asked me, okay, so this is maybe the big mystery of what's going on here, because obviously, we are training deep networks. So why are we succeeding in training deep networks? So there must be some magic property that enables that. Okay? So maybe if you asked me about 5-6 years ago, what's the biggest theoretical question, the biggest question about understanding why deep networks work, I would say that the biggest question is understanding this computational phenomena. Why is it that for many interesting problems, local search actually succeeds in training the network? We know that it will not always succeed. But I don't care that it doesn't always succeed. All I care about is it succeeds on the interesting problems I see, on natural problems, and whatever they are. And so there must be some magical property of such natural problems that make them trainable using a deep network. And I would claim that we don't have the faintest idea of what this magical problem is. Magic property is. So the only thing I can tell you that what this magic property is not. This magic property is not that you can represent the reality well using a neural net. Because we know that being able to be efficiently representable by a neural net is not sufficient to being able to solve this computational problem. That we have strong hardness results. So that means that if you ask somebody, why do you go to a vision person? I don't want to pick on anybody specific here, even though I know Ali would like me to. And you ask a vision person, you're using deep networks for your vision task. Why do they work so well? And the general answer you'd get is, well, the deep networks are very well suited to visual tasks because they can capture visual tasks very well, because you have low-level features and mid-level features, and that really means that I can capture this function that I'm trying to capture well using my neural net. What they're answering you is the second question here. They're talking about the expressive power. But that actually, I already know that neural nets have huge expressive power. That doesn't give me any information at all. All this explanation doesn't explain at all why neural networks work. Okay? Because as we said, being able to be expressed by a neural network is not the magic property. It does not provide any evidence at all that you can actually train a neural network. Okay? And so I hope this point is clear, because I think this is a central point. In order to understand why neural network works, we should not be thinking about why can we present things with a neural network. We should be thinking about why is it that local search actually succeeds in finding them, which are completely different questions. And one of them has essentially no bearing on the other. Okay, so as I said 5 years ago, I would probably stop the talk here, or I probably would not stop it here, but talk about work and trying to understand this phenomena of local search working and trying to uncover this magic property of what makes local search work. But about 5 years ago, we did an experiment that really changed my view, not only my view of deep learning, and this is actually not too different from the experiment mentioned before that Ben and co-author did 2-3 years ago, and I think Peter also actually had several similar observations a good decade and a half maybe earlier. So what we did is as follows.
1998.
What?
Peter Bartlett?
Yeah.
1998.
Yeah, 96 I think even.
There we go.
Yeah, so I then can calculate decades. I guess that's 2 decades? Yeah? So, yeah. Okay. Anyway, and I should say all these experiments are subtly different also, and it's not important for the discussion here. So the experiment we did is as follows. So what we did is we just trained networks of different sizes, and we're really trying to understand this computational phenomena of how is it that local search becomes easy, and trying to understand this overparameterization, how overparameterization helps computation, helps the search. And so each of these lines, this is not time on the x-axis, this is just completely independent trainings of larger and larger networks. And the black line is the training error. And in fact, the training error, as I have a larger and larger network with larger and larger capacity, it's easier to optimize, right? It's easier to find your way, and it's also just easier to fit data. And in fact, the training error decreases, and lo and behold, this is an MNIST, I think, we did it in several different data sets. The training error with 64 units, we already get 0 training error. Great. So we understand how we actually can get, we want to try to understand how local search finds this solution. But what's more interesting is to look at here in the test error. So the question, how does the test error behave? So as we decrease the training error, the test error also behaves because we have a bit better fit. And the question is, what happens when we increase the network size even more than that? So our traditional view of learning would say at this point, we're not improving our approximation error, we're fitting the data just fine, but we have more and more and more parameters, so we should be hurting our estimation error, and we should be seeing these U-curves that we show our students in the Introduction to Machine Learning courses. We should start overfitting. Okay? But this is actually not what you observe empirically. What we observe empirically is the test error continues decreasing. So we're actually generalizing better and better. We have less estimation error as the number of parameters increases. Okay? So what's going on here? What's going on here is that what's really controlling the complexity or our capacity is probably not the number of units. If we had to rely on the number of units for capacity control, then we should not, things should have been going up. More than that, if we look at networks with 1,000 units. So for this example, networks with 1,000 units already have more parameters and examples. Okay? With more parameters and examples, I cannot generalize. There are many, there's absolutely no way I should generalize. Why am I generalizing at all? Okay, so I'm seeing here, two phenomena. A, I'm generalizing, and B, I'm also generalizing even better than I am with less parameters. So let's take a closer look at that and look at these networks with 1,000 parameters. So the solution we found has 0 training error and actually generalizes well. But the thing is, with 1,000 parameters, you can it is actually possible to overfit the data. Okay, sorry, not 1,000 parameters. 1,000 hidden units. Number of parameters is much higher. It is possible to overfit the data, and the reason is that there are actually many ways of getting zero error solutions. Right, this is a completely underdetermined problem. Okay, and so there are many other zero training error solutions. Okay, that do overfit, and I'm plotting them here. Each one of these red dots is a zero training error solution. And I should emphasize the only thing we did in this experiment is just minimize the training error. Okay? So all of these are also completely valid answers we could have gotten back from our optimizer. And what I'm showing you here is their test error. So some of these actually generalize, the one we found generalizes well, but many of the others do not generalize well. Okay? So what distinguishes between them? So what Peter could have told you back in the 90s is that, well, again, it's not maybe the number of parameters, but maybe it's a measure of the size of the parameters, some norm of the parameters. Okay? And so we can check, maybe indeed it's the case that those solutions on the right there are zero training error solutions, but they have higher norm. Okay? Whereas our solution that we found has smaller norm, and because of that, it's generalizing. Okay? So they were uncovering here a different form of complexity control. And the big question here is, what is the norm we should look at? What is this complexity control? And we still don't know that question. What I'm plotting here is the path norm, which is some norm. I should say that if you plot just the standard Euclidean norm, you would not get such a nice plot here. So it is important what you plot. But at least for some norm that I plot here, I do in fact see good correlation between the path norm, the norm I'm plotting, and the generalization, which suggests that maybe the true complexity control here again is this path norm. Although I know it's not the path norm, but it's, because unfortunately correlation does not imply causality. But this is kind of the type of picture we'd like to see. Okay, so again, so if we take this point of view and think that the true complexity control is not the number of parameters, then what is the true complexity control? Which norm or measure of the weights or something actually controls generalization here? But then there's also another question, which is, I told you that the solution with small path norm actually generalizes well, and the solutions with high path norm, even though they're again completely legitimate zero training error solutions, do not generalize well. But how can we actually find that solution? Right? So I didn't actually minimize the path norm here. All I did was just ran gradient descent on the training. Okay, so I just minimized the training error. So somehow the training algorithm itself biases me towards a solution that has smaller norm or smaller complexity. How is that happening? Okay? And again, where is it biasing me? We don't have, I would like to get an understanding of where the optimization algorithm is actually biasing me. But also what we're seeing here is actually all the complexity control, which is really all the learning, is happening just by virtue of the optimization algorithm. Because if I just set up the optimization problem, which is minimize the training error, I could have gotten any of these valid solutions up there that would generalize horribly. So all the generalization, which is really all the learning, is coming just by virtue of the choice of the specific optimization algorithm. The fact that I use gradient descent and not some other crazy optimization algorithm that would give me those solutions. So that means that if I change my optimization algorithm without changing the learning problem at all, having the same formulation exactly, just change the algorithm in which I minimize the training loss, might give me actually different generalization properties. Okay? And you can actually see that. So here, we have an optimization algorithm that is based on this path norm that I said before. It doesn't matter, the details of the algorithms don't matter. Just think of it, I have two different optimization algorithms, the blue algorithm and the red algorithm. Okay? And both of them are completely valid optimization algorithms. On the left, we see that actually this is a function of time. On the left, we see the actual optimization objective, the training loss, which is what I'm trying to minimize. And both of them get to a global minima of the training loss. How do I know it's a global minima? It's zero training loss. It's definitely the global minima. So both of them get to global minima, but they get to different global minima. Okay? The blue optimization algorithm, path SGD, okay, gets to a better global minima. Better in what sense? In terms of, if you put on your optimization hat, it's not any better, it's just a global minima. They're both the same, they're both global minima. They both have zero loss. But it's better because it generalizes better, as we see on the right plot, shows us the test loss here. Okay? So again, we changed the optimization algorithm in a way that didn't change its optimization property, what completely changes what happens in terms of learning. Again, we can see here comparing SGD and Adam. Again, just two different optimization algorithms. You don't have to know what Adam is. Just think of it as the blue optimization algorithm, the red optimization algorithm. And here we see that if I put on our optimization hat, then we should look at the left plot, which is actually the training objective, what we're actually trying to minimize. And the red algorithm is actually better. Both of these algorithms would eventually get to what is probably the global minima, but the blue one will get there much slower. Okay? So in terms of optimization, the blue is worse, but if I look in terms of generalization properties, the blue one gets me to a better global minima than the red one. Okay? So we see here that much of the generalization is just happening by virtue of the optimization algorithm. In fact, I would argue that all the generalization is happening by just the virtue of the optimization algorithm, because with a really bad optimization algorithm, again, bad not in terms of optimization, with some optimization algorithms, I could get no generalization at all. I can get any fit I want. I can completely overfit the data. The problem is completely underdetermined. So that really means that all of our, sauce of what actually happens, all of our learning rule, everything that actually determines what is the inductive bias we're going to use, what is the learning rule we're using, is all hidden in the choice optimization algorithm. Right? So when you see a typical paper, typical learning paper, deep learning paper, roughly looks like this. Suggests some kind of very sophisticated model that we can explain how this model really captures reality very well. It's a really good model. It's really great. How are we going to train this model? Or it's very easy. We're just going to train this model by minimizing the training loss on the model. So this is our learning rule. And okay, we're going to do this somehow. There's details in appendix, or maybe not even appendix, just in the source code. Okay? And what I'd claim is that the learning rule here is not specified in sections 1 and 2. The learning rule is not specified by the fact that you're solving this optimization problem, because the optimization problem is probably underdetermined. It has many solutions that are not going to generalize well. All your learning algorithm, all your inductive bias is in this dot there in section 3 that's not even explicitly specified and we don't even think about. Okay? So really you should think about it in the following way. You're minimizing here. We're looking at huge models. And I would argue that the models we're looking at, really you should think about it as infinite models. They have so many units that they really behave the same as infinite models. The only reason we're using a finite number of units is because we're using computers that have a finite number of bits. It's the same reason that we represent. So how many of you are using computers to do calculations in real numbers? Okay, that's none of you are, right? Because all of you are actually using computers to do calculations in some 64 or 128, and I don't know, bit representations of real numbers. Why are you limiting yourself to 64 bits or 128 bits? You're not limiting yourself to 64 bits because you think that 64 bits is going to make the calculations better. You're just limiting yourself to 64 bits because you think that 64 is close enough to infinity in the sense that it can capture these real numbers which are really infinite objects. Okay? In the same way, when you're using a neural net with some number of units, the number of units is not giving you any learning power. Okay? The number of units, you're just using a finite number of units because you're using a finite computer, and that's the largest number of units you can represent in a computer. You get a bigger computer, you probably use more units. Okay? And that's really what's going on here. So we have really infinite size networks, and so we can represent any function. Okay? So really the network, the model itself doesn't provide us any type of inductive bias. Okay? We have the space of all functions. And so let's look at the error landscape. There are many, if we look at the optimization error, the training loss, there are many global minima of the training loss. Okay? This is fitting the data perfectly. There are many ways of fitting the data perfectly, and you should think of these as oceans of your optimization landscape. Okay? And so you're going to start optimizing and you're going to end up in an ocean. Okay? But where are you going to end up? You're not going to end up in the middle of the ocean, right? You're going to do some local search and you're going to end up on some beach. But which beach are you going to end up on? So if you start optimizing here, you're going to go down, you're going to end up somewhere in the Atlantic or some bay or something. If you start optimizing in Berkeley and going to optimize, you're probably going to end up in the San Francisco Bay. Okay? What happens if you start optimizing in Chicago? Okay, so Chicago is so flat that the rivers flow backwards, right? I mean, you can get pretty much, you can go get pretty much anywhere without ascending, okay? So now it really depends what your optimization algorithm is. If your optimization algorithm likes going south, you're going to again end up in the Gulf of Mexico. If your optimization algorithm likes going east, you're going to end up somewhere in the Atlantic. If your optimization algorithm likes going north, you're going to end up somewhere in, the St. Lawrence or something, okay? And so all the choice of which global optima you're going to get to is an optimization algorithm. Okay? And the geometry of the optimization algorithm, which directions does it like going, is going to determine so it's going to end up in the nearest beach. And this notion of nearest beach depends on the geometry in your optimization algorithm. And this choice of geometry in the optimization algorithm really determines everything that's going on in deep learning. Okay, let me try to make this more concrete. I don't know how much time I have, but it seems that I'm not going to care. And show you several examples that's going to make this more concrete of how we can really generalize in these overdetermined models and how we should study things. So the first example is not on deep learning, it's just on metrics completion problem. So I have a partially observed matrix and I want to complete it. How am I going to do that? I'm just going to take, try to fit a matrix X, full dimensional n by n matrix X. And what I'm just going to do is I'm going to minimize the error to the observed entries. So you should all recognize that this is a completely stupid problem. Okay, doesn't make any sense. Okay, the problem is very overdetermined, right? In particular, I can complete the observed entries and put zeros everywhere else, or complete the observed entries and write the Fibonacci sequence everywhere else. Okay, there's no way here to generalize, and this problem doesn't make any sense whatsoever. Okay, how am I going to solve this? The way I'm going to solve this is I'm going to make it even more underdetermined. Okay, I'm going to make it even more overparameterized by writing x as u times v. So instead of having n squared variables for much, much fewer observations, now I have 2 n squared variables to much, much fewer observations. Okay, just made the situation worse. Okay? So again, this is just as senseless as before. I can represent any matrix as u times v. I did not limit the my choice of model, so my choice of model here is writing x as u times v, did not at all limit the set of functions that I could represent. Okay, nevertheless, we're going to see that this choice of model is going to do something interesting here. So what we're going to do, even though this is a completely stupid, senseless problem, just like deep learning, we're going to solve it using a very naive algorithm, which is gradient descent. So what happens if I optimize this with gradient descent on UV? So let's try it out on some data. So we generated some data from an approximately low rank metric, something that says we have some chance of reconstructing. And what you see here is what happens when you do gradient descent on X as opposed to gradient descent on U and V. So if you do gradient descent on X, not surprising, nothing good happens. Well, what's nothing good? Well, first of all, we find the global minima. Okay, so we find a zero training error solution. We fit all the observed entries. Big deal. It's very easy to fit all the observed entries. And how well do we do in unobserved entries? Well, we do horribly. This is our tall bar here. The test error doesn't do anything. Not surprising. What happens when we do gradient descent on U and V? Well, we also succeed in fitting the observed entries, but now, surprisingly, we actually generalize pretty well. We get a very good test error on those unobserved entries. So it actually seems like we did something here. More than that, let's tweak our optimization algorithm. Instead of doing gradient descent with exact line search, which is what I did here, let's do a slightly worse optimization algorithm, which is gradient descent with a fixed small step size. So this is going to take longer to converge. It's a worse optimization algorithm. But when we do that, it actually generalizes even better. Okay? Just like we saw before, change optimization algorithm, we change the optimization properties. So what's going on here? So in this case, the reason I'm showing you this is we understand what's going on to a large extent. And what's going on here, I can tell you what is the inductive bias introduced by the optimization algorithm. So again, the optimization algorithm is going to find a global minima, but it's not going to find any old global minima. It's going to find a very special global minima. The global minima this optimization algorithm is going to find is the minimum, is not any solution, but the minimum nuclear norm solution. Okay? So it's going to find a very specific global minima, and we have lots of work already that we know that we had before this, coming from a theory of matrix completion and matrix reconstruction, of how minimizing the nuclear norm is a very good inductive bias, and in particular, minimizing the nuclear norm, you can get generalization guarantees and can succeed in reconstructing approximately low-rank matrices. Okay, so here we have a complete understanding. We did not make an explicit assumption about the data. We used a completely overdetermined, completely senseless model, optimized it using local search, and we saw that it actually corresponds to doing something very sensible that we didn't say explicitly what it was, but we can understand after the fact. You can use theory to understand what we're doing. And that thing actually makes sense. Okay, now let's go to deep learning. I'm going to wrap up soon. Okay, and in order to do deep learning, let's start with deep learning with 1 unit. Okay, and this is what, just as Matan, this is what Tommy already mentioned. If I have an overdetermined linear model, just 1 unit, and I'm fitting just one unit, fitting a linear model, an overdetermined problem, so I have data that's linearly separable. There are many ways of separating this data. I can separate it this way, I can separate it this way. If let's train the model with gradient descent, it's going to converge to one of these ways of separating it. Which way is it going to converge to? And what we can show, what is it going to converge to, is exactly the hard margin SVM solution, the max margin solution. And again, even though the margin or hinge loss or anything like that is not part of the formulation, it just comes implicitly from the optimization. Great, so that's 1 unit. That's not so interesting. What happens if we have a bunch of units? So we're going to look at a deep model, but still linear, a deep linear model, and optimize it. So it turns out, quite disappointingly, that at least for linear models, it doesn't matter how many units you have and how many layers. If you train it, you're going to still get to the same thing, which is the max margin solution. Okay, so it seems that in this case, this overparameterization doesn't help us. But let's go to a different overparameterization and look at a linear convolutional network. So here, at each layer, so all the units are still linear, but at each layer, what I'm doing is doing a convolution of the previous layer. Okay? Okay, so this is still just an overparameterization of linear models. What I can represent here at the end is just linear functions. So I'm just still learning a linear model, I'm learning a linear function, but I'm overparameterizing it in some strange way. And now I'm going to optimize it with gradient descent, and lo and behold, I actually get very interesting inductive bias. What happens here is what I'm going to converge here is to a linear predictor that has minimum L1 norm in the frequency domain. Okay, so I'm getting sparsity in the frequency domain. That's with one hidden layer. If I have a bunch of hidden layers, I'm going to get even a better sparsity in the frequency domain. I'm going to be implicitly minimizing the bridge penalty in the frequency domain for LP where P goes to 0 as the number of layers increases, right? So again, we get, just by changing the parameterization here, without changing the model class at all, we introduced very interesting inductive bias that we can understand how it generalizes. So again, we see here that the effect of parameterization here is not changing the model class. In both of these examples, our model class was essentially everything. For matrix completion, it was all matrices. For these linear neural nets, it's all linear functions. But just by changing the parameterization, we change the geometric structure of our local search, and then we're changing our bias. As the last example, let's see what happens with a deep nonlinear model, or at least depth 2. And this is infinite width, so now we're talking about a two-layer network with infinite width and ReLU activations. So you can represent every function here. So you can think of this as, again, as some representation of any possible function. I'm just parameterizing the space of all functions, and I'm going to train this by gradient descent, or in this case, I think it's true with gradient descent. I can formally show this with a bit of weight decay. I'm going to train this model in this parameterization. I'm going to fit the data. But what is the inductive bias I'm introducing here? Any guesses? Okay. So the inductive bias I'm introducing here in function space turns out to be the total variation of the derivative, so the integral of the absolute value of the second derivative. So some control over curvature, which is a very natural inductive bias. And again, we can understand how is this maybe generalizes or not generalizes. And all of this comes just by changing the geometry of our search space. So, and what's going on here is that we said that the key component in my eyes in all this is thinking about the geometry of your search space, but there's the geometry in parameter space and what happens in function space. So in parameter space, you have some geometry, and that limits yourself essentially to, what you should think of is what is the ball under this geometry in parameter space. That's your essentially effective model class, what you should be thinking of the capacity. And that might be like a relatively benign thing. But once we go from parameter space to function space, that relatively simple benign thing can look very, very interesting. Okay? Can look like the set of matrices with low nuclear norm, or linear predictors that are sparse in the frequency domain, or functions with bounded total variations of their derivative, or all kinds of very interesting biases. Okay? And so I would claim that in order to understand really what's going on, we're learning with deep networks, we're learning with way over-parameterized models. Thinking of what the models can represent is meaningless. What we should think about is how does this parameterization bias us to particular things. At the very least, this would allow us to answer core questions like this question, which asks, if I just add a linear layer to my network, I didn't change my model class. Why should this be better? And there are all kinds of answers here that have nothing to do with, just complete, I don't want to say this word, okay? And now we understand why, why does just changing your parameterization without changing the model class, which is all we're doing in deep learning, actually helps us. Okay, so let me just end going back to my very first slide. I think Ali, this is exactly what you wanted, so give me another 20 seconds here. So we said that at the beginning I told you that the state of affairs of understanding deep learning is we understand expressive power and capacity, but the only thing we don't understand is computation. Okay? But that's a big thing. Okay? And we really want to understand what this magic property. What I think is the more correct view of modern deep learning is that we don't understand any of them. We don't understand capacity because we don't know actually what is the correct complexity measure to look at. We've been throwing around lots of suggestions, and I think Peter will try to address this in his talk. There's been lots of work in trying to come up with different complexity measures and trying to understand capacity control with respect to those complexity measures. Okay? So we're making progress on that. But then if we do understand this complexity measure, the even more interesting problem is the expressive power question. Okay? Now we should ask ourselves not what we can represent with a deep network, the answer to that is everything, but what can we understand with deep network with bounded norm, whatever that norm is, and I'm using norm here very loosely, with bounded complexity. And we have absolutely no idea what the answer is, because we have absolutely no idea what the complexity measure is. And again, I showed you today some answers that might arise. Like for example, we might say that we should ask is, what can you represent with bounded norm, with Rayleigh networks with bounded norm, and the answer would be, well, functions that have bounded curvature. Okay, that's a very different answer than you get if you ignore that. And so really we don't understand what's going on with expressive power. And finally, the optimization and computation aspect here is of course very important, even more important than before, because it's not only about when would the local search succeed, although that question is still very important, and that we know that what we should ask is also where would that local search lead us. Okay, so I'm going to end here. I'm only probably 40 minutes over time.
All right, he gets one question, right? One.
Yeah,
No?
go on then.
No? Not really.
Just go on then.
So I'll say that was a great talk, Nati. How about that? We'll start there. Yeah? No, I have a question. So do we know what good inductive biases would be you'd like to add to these models? And if so...
I don't think it's a matter of adding inductive bias. It's rather what I'm asking is what inductive bias you're actually using. And then maybe you can improve it. So these models obviously have very good inductive bias. Okay? They work well. It's an empirical statement. Okay? I would like to understand what is the actual inductive bias. And if I understand that, then maybe I could improve them so that it'll work even better, work in cases they're not working now. Okay? But the process here is a bit backwards. Usually we're thinking of a situation where I start with some inductive bias, and then I design my learning rule to have that inductive bias. Now I'm a bit of reverse engineering it.
Just a quick question. Sure. You started out emphasizing the role of optimization algorithms as being important in the solutions that we're finding in these situations. And I guess from my perspective, I'm not a very algorithmic type of thinker. So from my perspective, I was wondering, can't we alternatively just think about the initialization and the distribution induced by the random choice of initialization of parameters. So if you randomly choose your parameters, that induces a distribution over the function space that you're going to start from. And of course, if you change the parameterization, that changes the distribution. So in your case of matrix factorization or optimization, it seems like that's really the explanation, no?
No. So the initialization can play a role. And so if you're not an algorithmic person, then don't think about the algorithm, think about the geometry. Okay? So I think, sorry? So I think so I think what you should think of, I think the geometry plays a much stronger role than initialization. So in particular for the matrix completion problem, if you're looking at the squared loss, initialization is more important, but if, for example, it was a classification problem, so the entries were just plus minus 1, and I'm minimizing some kind of cross entropy, then actually the initialization plays no role at all. Whatever initialization is, I'd always get to the minimum trace norm, minimum nuclear norm solution as well. So what's going on is I'm not saying that the initialization is never important, but in high dimensions, from the low dimensional picture is a bit misleading. In one dimensions, if I use any descent algorithm, if I start from some point, it's clear which minimum I'm going to get to. Okay, I'm going to get the one which I'm in Bassanov attraction. In very high dimensions, most points are not in the Bassanov attraction of a particular local minima or global minima, but rather from the same initialization point, I can go to many different places. Again, think about Chicago. Okay? I can go without ascending. Okay? Again, this is only in 2 dimensions, so you can get very rich, but in many dimensions, all points everything is Chicago. So from the same initialization, I can go down to many different places, and the choice of which place I'll go to is determined by the geometry of my local search. And that plays a much more important role than initialization. So again, I can actually prove this and formalize it in some cases. If you want a concrete example, then both in actually all, well, the first two examples I presented, actually all three examples I presented, at least with the appropriate loss function, the initialization provably does not play a role. Like with probability 1, like as long as it's generic, right? Okay, so I don't know if, I hope that. Yes, okay.